So what you had in the morning? Which class you had in the morning? Today I had only one subject or two subjects, cloud computing and NFC. Okay. Okay. I think Sunday you have three classes, is it? So Saturday only one class. Am I right? Yes. Okay. Okay, guys. So what we have covered in the last class? So can anyone put a message on chat box? So what we have covered in the previous session? So we have started with the analytics concept, right? And we have started with big data analytics definition. And we have yet to start the definition, is it? Analytics, yeah, exactly. Hadoop architecture also we have started. And cloud computing introduction also I had given in the previous session. Am I right? Yes. Correct. So there is an activity in big data that is group self-selection. Yes, sir. Guys, yes, guys, I forgot to what inform you. Actually, for your assignment, you have a what lab experiments. So there you have to solve or you have to submit your assignment group wise. Okay, since you have to solve everything group wise, you have to create your groups immediately. Okay, you have to select your group immediately. So minimum of 3, maximum of 4. That is this team size. I think already you have got circular, right? Yes, quiz 1 we are going to start on September 1st. And syllabus for quiz 1 is session 1 to session 5. Tanya. So it is objective quiz MCQ for 5 marks. Guys, in your EC1, you will be having 2 quizzes, 1 assignment. So assignment I'm going to give you after after your midterm examinations. So maybe after 10th session. So I'm going to upload assignment 1. So before that you will be having, before your midsum you'll be having quiz 1, and after your midsum you'll be having quiz 2 and 1 assignment. Only 1 assignment I'm giving you according to your handouts. Okay. So after 10th session, so we are going to release assignment 1. So it is on lab actually. It is completely practical. So before that, I'm going to take some what lab session, and I will explain you how to solve that. Is this clear? Is this clear to everyone? Questions also are mentioned in the circular, right? So totally you'll be having 20 questions. 20 questions, 40 minutes for 5 marks. Okay, no negative marking. No negative marking. Guys, totally 10 marks for your quizzes. So 5 marks now in quiz 1, 5 marks in quiz 2, and 20 marks for your assignment. Any doubts? Okay, guys, now time is 5:52. So let us start with today's session. Okay, let me share my screen. Okay, guys. So as usual, I welcome you to what session 4. Actually, this is session 5. In session 5, I'm covering session 4 concept, guys. So good evening once again and warm welcome to our fourth session on big data systems. And it is great to see all you here. So I think you people are ready for today's concept. Okay. So as usual, guys, so before I'm going to start my session, so I'm going to share one thought with you people. So today I've selected this thought. Okay. So the only way to do great work is to love what you do. So my dear friends, the word of big data is not just a subject to learn. Okay. So it is a field of immense possibilities, and the passion for it will true set you what apart. So with that spirit, so let's get started with today's session. So this is the agenda. I think last class we have left with a few slides, right? So so in today's session, so first we will talk about the characteristics of big data system. So specifically focusing on how they handle failure and the concept of reliability and availability. So this is basic for session 4. And these are not just a technical terms, guys. So they are critical design considerations for any large scale system. Okay, so that you should understand. So after that, we will move to the next one that is called as consistency. So consistency is very important for session 4 concept. Already I've told you, right? So in CAP theorem, we are going to use the concept of consistency. So that is very much important for us. Okay, so let's move to the very first slide. Let's move to the very first slide. Yes, guys, last class we have started with distributed computing, right? Okay, so let's talk about a reality of distributed system. They fail. Okay, so this slide highlights a very important points. What are those? So look at here, guys. The very first point, what it is saying, failures of nodes and links is a common concern in distributed system. I think everyone will agree with my point. So unlike a single monolithic server, a distributed system is made of many components. Okay, so it will be containing nodes, networks, disks, and any other of them can fail at any time because it is connected through network, right? So what is our approach? Then what is our approach, guys? So it's essential to have fault tolerant aspects in design. Guys, you cannot simply hope that nothing will ever go wrong. A robust system is one that is designed to handle failures gracefully. So what do you mean by fault tolerance? So you can ask me a question, right? So it is a measure of how distributed system functions in the presence of failure of the system components. Okay, so think of it like this, guys. A great race car is not just fast. So it is designed with safety features and redundancy so that even if a part breaks, the car can still finish the race or at least not crash catastrophically. Correct? No? The tolerance of these faults is measured by two key parameters. What are those? First one is reality and second one is availability. Maybe you have heard about reality and reliability and availability in the previous session. Guys, reliability is an inverse indicator of failure rate. Correct? No? So it is inverse to what? Failure rate. So it answers the questions. So how soon will the system fail? Guys, a reliable system is one that just keeps working without breaking down. And availability is also very much similar to that. Okay, so it is an indicator of the fraction of time a system is available for use. Reliability, see guys, what you have to understand here in simple terms, it is the percentage of time the system is up and running. Sometime we are going to say 24/7. So 24/7, the system is available means then it is called as an availability. A system is of course not available during a failure. Okay, so these two metrics might sound similar, but they are distinct. So reliability is about the time between failures, while availability is about the total uptime. So this is the small difference between these two. And next slide, you just observe here, guys. So now I was talking about metrics, right? So let's get a bit more quantitative. Okay, so this slide introduces some key metrics for measuring reliability and also availability. So these are not just abstract formulas. So they are used by companies every day to set service level agreement. Try to understand this. So this is every day used by companies actually. Service level agreement. For SLA, they are going to use it. Okay, and by using this, they are going to evaluate performance of their system. Okay, so first, what do we have here? So first we have MTTF. The meaning of this is mean time to failure. Okay, so this is the average time a system operates before it fails. The formula for this is MTTF is equal to 1 by failure rate. 1 by failure rate. So this is an average value, guys. So try to understand this. So this is an average value. A simple way to think about it is a total hours of operation. See, this is another way of what understanding. Total number of hours of operations divided by the total number of failures. This is total number of units they have mentioned here. So it is nothing but total number of failures. Understanding my point, guys? Next up, what do we have next up? So next we have MTTR, right? MTTR, right? So mean time recovery or repair. Mean time to recovery or repair. Guys, this is the average time it takes to get the system back up and running after a failure. Okay, so it is the total. See here, clearly mentioned. So it is the total hours of hours for maintenance divided by the total number of repairs. Total number of repairs. So this is the formula for MTTR. Okay, a related metric is, now we have a related matrix. That related matrix is called as MTTD. So mean time to diagnose. So this is the time taken to what? Figure out what went wrong. Okay, so for our calculation, we will often assume this is 0 unless specified. So, so for our calculation, we are going to consider this as a 0 value. And finally, we have MTBF. So mean time between failures. So mean time between failure means what, guys? This is the total time between two failures. Try to understand. So total time between two failures. The relationship is very simple, guys. The relationship is mentioned by using this formula. So MTBF is equal to MTTD plus MTTR plus MTTF. So it is the sum of the time the system is running correctly and the time it takes to diagnose and repair it. Guys, understanding these metrics is crucial for designing fault-tolerant system. A high MTTF and a low MTTR lead to highly available system. So which we will see more on later slides. So hope this is clear to everyone. Shall I get quick confirmation? So till here everything is clear. All these formulas are clear. So better you all take down the snapshot, guys. That snapshots are very, very important because I'm going to solve one problem on this. Okay. Okay. Now look at here, guys. Guys, you can observe here. So now we are talking about reliability, a serial assembly. So before that, am I left anything in the previous slide? Okay, so here we have left something, right? So here we have a diagram. So this diagram we have taken from the what? Internet. So here you can observe. So this is clarifying the what concept we just discussed. So you just to take up a look at the what this diagram, guys. So here we have correct behavior for period of time. So which is our MTTF, Then we have first failure. See here, we have first failure occurs. So what happened next? The clock start on the repair process. First, we need to diagnose the problem, right? So first we have to diagnose the repair actually. So diagnose the failure actually. Okay. So which is our MTTB here? Okay, that is mean time to diagnose. So once we know what is wrong, so we proceed to repair. Okay. And which is our MTTR in explanation what I have given. And after repair is complete, the system returns to correct behavior. Correct behavior. So making the what start of new MTTF period leading to the what second failure. The total duration from the first failure to the second failure is the MTTB. Oh, sorry, MTBF. So from first failure to second failure, this time distance is called as MTBF. Try to understand this. Okay, so clearly you can see the relationship. So MTBF is equal to what? MTTD plus MTTR plus MTTF. Correct? No? The same thing we have taken here. So this diagram perfectly illustrates the entire life cycle of the failure event. That's all. Okay. So now let us move to the what next slide. See, next slide we are talking about reliability. I have told you, right? We are going to talk more on reliability. So here we are talking about reliability. So look at here, guys. You can see we have mentioned a keyword serial assembly. So serial assembly of components. So what does a serial assembly mean? Guys, it means all components are arranged in a sequence and the failure of any one component result in the system failure. Try to understand this. So failure of any components results in the system failure. So think of a chain. Okay. So if even one link breaks, the entire chain is broken, right? So this is a very common scenario in many systems. See, for example, if a web server, a data server or load balancer are all required for an applications to function. So they are essentially in a what serial assembly from the user's perspective. Okay, so you can observe here. So I have taken one diagrammatic representation. What this diagrammatic representation is saying. So see, look at here. A system C composed of two components. What are those two components? One is A, another one is B. So this is connected in series, right? Look at here. It is connected in series. So the MTTF of component A is MA here. We have mentioned it as MA, and the MTTF of B is mentioned as MB. So what's the overall MTTF of the system? What is the overall MTTF of the system C? The failure rate of the system is the sum of the failure rate of the individual components. So remember that failure rate. So is 1 by MTTF, correct? No. So that's why failure rate of C. Let me write here. That is not okay. Here it is clearly mentioned. So failure rate of C is equals to failure rate of A plus failure rate of B. That is equals to 1 by MA plus 1 by MB. Correct? No? So what it is giving us, guys, what it is giving us. So this gives us the formula for the what? Systems MTTF. So MTTF of system, that is equals to 1 by sum of, see here, 1 by sum of 1 by MTTF I. So this is for all components. So here we have taken only two components. This is for all components. Correct? No? You're all agreeing with my point? See, for an example, the MTTF of C is 1 by MA by plus 1 by MB. So this is a very important point, guys. So it means that in a serial system, your overall reliability is always worse than your least reliable component. Okay, you are only as strong as your weakest link actually. Now, what about opposite scenario? Okay, what is the opposite scenario we have told? So we have told about parallel assembly, right? So this is about serial assembly. So now let us discuss on parallel assembly. Let's talk about more desirable scenario in the what distributed system, that is called as parallel assembly. So this is a key concept in achieving fault tolerance. So in parallel assembly, you have multiple components. Okay, so that perform the what same function, and the system only fails if both A and B fails. So think of a cluster of nodes, guys. If one node goes down, the others can take over its workload. Correct, no? And the system as a whole remains operational. So this is a prime example of redundancy. Okay, so you can see here. So here we have a system C, again, which is containing what component A and also component B. So which is running in parallel, not serial. See, look at here. So it is running in parallel. The MTTF of component A is MA here. The MTTF of component B is MB here. So this is MB, guys, not MA. Okay, this is MB. Okay, MTTF of the system is the sum of what? MTTF of the components, correct? No. So the MTTF of C is equal to MTTF of A plus MTTF of B, because both A and B have the fail for C to fail. Correct, no? So this gives you the what? Much higher overall MTTF, and as a result, a much more reliable and available system. This is the principle behind many fault tolerant architecture. Okay, like active, passive setups. So which we will discuss shortly. So this is why we build clusters. We don't just add nodes to increase the processing power. We add them to increase reliability and also availability. That you have to understand. Okay, so next slide, I'm going to explain you more on this. See, look at here. Now I'm trying to explain you the availability. So if you have any questions on reliability, please do ask me, guys. So I'm jumping into availability concept. Sir, why the formula I've shown you, right? 1 by MTTF. So why you're asking this question again? Have you seen the formula? So I've shown you in the previous slide, right? So that's why you have to listen, guys. You have to listen everything carefully. So look at here. What failure rate we have taken here? Failure rate is equal to 1 by MTTF, right? Correct, no? You're understanding. So why it is 1 by MTTF? So listen to me carefully, okay? So each and every points are important because we are solving one numerical problem here. So yes, guys, now we are talking about availability. Okay, so let's tie everything together and look at what availability. So this slide presents the formal definition and crucial formulae. What is availability? Availability is equal to time system is up and accessible by total time observed. So this is a simple intuitive definition. It is a ratio often expressed as a percentage that tells you how often your system is working. So we can also express availability using metrics we just learned, guys. What is the formula? See, this is the formula we can use here. This is the formula we can use here. Availability is equals to MTTF by MTTD plus MTTR plus MTTD. Correct, no? And since we know that MTBF. Okay, let me write here. So MTBF is equals to MTTD plus MTTR plus MTTF. So we can simply, this means we can simplify this to availability is equal to MTTF divided by MTBF actually. Correct, no? So this completely what replaced by MTBF. Look at here. So this formula is very powerful. It tells us exactly how to make a system highly available. A system is highly available, then MTTF is high and MTTR is low actually. You can ask me why it is high or why it is low, right? The meaning of the very first one is the system does not fail very often. So you can achieve this with high quality, reliable components and also good design. But why MTTR is low? This means when a failure does happen, you can fix it very quickly. So this requires good monitoring, automated recovery, and also well-documented procedure. Guys, this is very, very important concept. The 4 9s. Okay, the 4 9s are 5 9s of availability that companies boast about 99.99% or 99.999% are all derived from this formula. So to get to those numbers, you need a very high MTTF and very, very low MTTR. So this is very, very important. I'm marking this as a very, very important one. Understanding my point, guys? So let's quickly take one example. Okay, this is the example given. So I think one example is given in your previous year question paper also. So that problem you can take as a homework problem. So let me solve this problem first. So later you can solve the question paper problem. You can take question paper problem as a homework problem and you can solve later. Try to understand this problem. So let's apply the formula to real world scenario. So this is the classic problem that a system administrator or big data architect would face. Okay, so here is the problem. A node is a cluster fails every 100 hours. Listen to me carefully. A node in a cluster fails every 100 hours. So this is our, what is this, guys? What is this 100 hours? Can anyone tell me? So this is nothing but MTTF. See here in given I have written, in solution I have written. So this is given. So MTTF is equal to 100 hours. You're all getting my point. Now what about the recovery? What about the recovery? Guys, on failure, listen, look at here. On failure, the whole system needs to be shut down. The faulty node replaced and the system restarted. So this takes 2 hours. Look at here. This takes 2 hours. Additionally, the applications needs to be restarted, which takes 2 hours. So our MTTR, that is mean time to repair, is the sum of these 2 times, right? Sum of these 2 times, right? 2 hours plus 2 hours. So which is MTTR is equal to 4 hours. So that is also calculated here. Okay, so for this problem, we will assume the time to diagnose is negligible. Time to what? Diagnose is negligible. So that we have taken 0, right? I have explained you already. Now let's calculate the availability. So how do you calculate availability? So we have a formula, right? So availability, what is the formula for availability? Availability is equals to MTTF divided by what, guys? MTTF plus MTTR. So one more is equals to 0. That's why I'm not taking one more. So MTTF by MTTF plus MTTR. So what is MTTF is equal to? MTTF is equal to 100 divided by, so this is 100 plus MTTR is equal to 4 hours. So that is equals to 4. So totally this is equals to how much, guys? 100 divided by 104. See, this is I have taken here directly. And that is equals to 96.15. Correct, no? 96.15%. Think about this, guys. At first glance, 96.15% might seems pretty good, right? But let's look at the what financial impact. The problem states that the downtime cost. Look at here. If downtime is $80K per hour, then what is the yearly cost? Guys, to find yearly cost, we first need to find the total downtime per year. That is very, very important. Correct? No? We have to calculate total downtime per year. That is very, very, very important, right? Not per year, per hour, sorry. It is given as a per hour. So we have to calculate per hour. To find the yearly cost, we first need to find the total downtime per year. The system is down for 4 hours, right? For every 104 hours of operation. So the percentage of downtime is, what is the percentage of downtime? So percentage of downtime is equal to 4 by 104. So which is approximately equals to what, guys? 3.85 percentage. So 4 by 104 means that is approximately equals to 3.85 percentage. The total hours in a year are, what is the total hours in a year? How much it is, guys? 365 days into 24 hours, right? So 24 hours per day. So this is what we are going to take, guys. 24 hours. Let me write it. This is days. Days equals to 24 hours per day. So yearly downtime cost is equal to $80,000 into 3.85 percentage of hours into 365 days per year into 24 days per hour. That is all divided by 100. Correct? No? That is all divided by 100. Correct? No? Yes or no, guys? So finally, what you are going to get? So finally, you are going to get 27 million. So that is in USD. That is in dollar. Okay, guys, this is not just an academic exercise. Okay, a seemingly small drop in availability can have what? Massive financial impact for a business. Is a small amount, guys. Is a small amount. So this is why companies invest so much in building robust fault tolerant systems. So now we are all understanding, right? What is the importance of this? So now we are all understanding, right? What is the importance of this? Yes or no? Can I get quick confirmation on chat box? Is this clear to everyone? Can we calculate the downtime like below? What is that 100% minus availability? What is 100% minus availability? So directly you are calculating it to 94, 96. Then why I have given formulas? So you have to take the formula and you have to calculate. See, guys, this is, I told you right at the end. So this is very, very important task in business. So that's why every company are investing money on calculating availability and also reliability. So hope this is crystal clear to everyone. Quickly, guys, quickly, I want you people to respond. I don't want to waste time here. So already we have spent 30 minutes, but still we have not entered into a what? 5th session concept. Okay. Yes. Now look at here, guys, fault tolerance configuration and standby options. Friends, the high level concept of fault tolerance is great, but how do we actually implement it? So this slide shows us 4 common high availability model, also known as standby configuration. So this is called as standby configuration or standby option. Guys, look at the table. So this table is a great way to compare them based on secondary node behavior, data protection, and failover time. Okay. So notice the trade-offs. What are all trade-offs we have used here? Cost decreases, the failover time and MTTR and tends to increase. Okay. Okay, look at the very first one, guys, load balanced. The very first one we have considered as load balanced. So in this model, both the primary and secondary nodes are active. Primary and secondary, both the modules are active. Nodes are active and serve request in parallel. So data is replicated bidirectionally. See, look at here, I mentioned data is replicated bidirectionally. So the key advantage here is zero failover time. Zero failover time, because both systems are always working, right? So this is the what most expensive, but also the what most highly available option. And what is the second one? Second one is hot standby, or we can call it as active passive. aka active passive. It is also called as aka active passive. So here secondary node is up and running. Okay, secondary node is up and running, but it is passive. So it does not process request unless the primary node fails. So here in this case, data is replicated and kept identical on both the system. So in this case, failover is very fast, just a few seconds, because the secondary node is ready to go. And what is the next one? Next one we have warm standby. So here also, guys, the secondary server is up and running here. Secondary server is up and running here. But the software components are only started when a failure occurs on the primary. So data is regularly replicated and stored on a shared disk. So in this case, the failure takes a bit longer, a few minutes. So as the applications need to be what started here. And finally, we have cold standby. So this is the what most basic and least expensive option. The secondary node is only installed and configured after the what primary fails. So in this case, data is backed up on a storage system, and failover can take very long time, few hours. They have mentioned it as a what few hours. So as the entire system needs to be what set up from the scratch. Guys, this is a what great slide for you to what understand the cost benefit analysis of different fault tolerant design. Okay, on the next slide, we will see visual representation of active and active passive configurations. Okay, now you can see here. Okay, this slide is great visual to what help you to understand the difference between active and also active passive. So which are the what most common configuration we just discussed. Okay, on the top you can see here. So we have the what active model. So you can see the load balancer. This is the load balancer. The load balancer distribute request from multiple client to two separate HTTP server. Look at here. So we have taken multiple requests and it is distributing to two different HTTP servers. So both servers are active and handling traffic simultaneously. Guys, this is the load balanced model we just talked about. If one server goes down, the load balancer simply routes all the traffic to the other server. Correct, no? Because it is already active and the failover is instantaneous. So now look at here, passive, active, passive. The second one is called as active passive model, right? So here, all the client requests are directed to a single primary server. See, we have only one server here, guys. So everything is going to what? Only single server. So there is a what second server. That second server is called as, see here, sorry. This is the primary server. This is the secondary server. Okay, so server one. And there is a what secondary server also, which is a failover server. That is called as a failover server. So see, it's up and running every time, but it is not active serving traffic. So if HTTP server 1 fails, the system automatically switches all the traffic over to the what? HTTP server 2. This is the hot standby model. I have shown you, right? Previously, I have shown you, right? So this is hot standby model. Guys, the warm and old standby models are variations of the what? Active passive model. The difference lies in how the passive or failover node is kept updated. Guys, what you have to understand here is with a hot standby, data is constantly replicated. With the warm standby, replications happens less frequently. And with cold standby, there is no live replications at all. You are working from a backup. So this visual clarifies the differences and the trade-offs we talked about. Now let us look at what some other cluster topologies. Okay, let's look at the what some other cluster topologies. Okay, so let's extend our understanding of fault tolerant cluster by looking at some common cluster topologies. What is the first one we have mentioned here? First one is n+1. Guys, in this setup, so in this n+1 setup, you have n number of active nodes and one dedicated standby node. Understanding my point, guys? N number of active node. So that is the meaning. n+1 means n number of active node and one dedicated standby node. So this, single standby node is configured to take over the what role of any of the n primary node if they fails. So this is a what cost effective approach for single point of failure. I think everyone will agree with my point. Then what about second one, n+m? So n+m here. So this is the extension of what? n+1 model. So you have n active nodes and m standby nodes here. So you would use this if you want to anticipate multiple failures. So which is especially important when running many different services in a what larger cluster. And next one we have n2 1. So this is a classic failure model. The secondary failure node is a temporary replacement. That's it. So once the primary node is repaired and restored, the services are reactivated on it. Okay, so this is useful for systems that require a specific highly configured primary server. And next one, n2n. What is the meaning of n2n? So in this model, there is no special standby node. There is no special standby node. So when any node fails, the workload is simply redistributed to the remaining active nodes. So this is a very common design in modern scalable big data system. Okay, so this is very common in big data system. Try to understand this. This node, this is very, very important for us. Okay, so guys, actually we have used this in Spark, where nodes are considered commodities and failure is a normal occurrence. Clear? So each and every points are clear. So now we are talking about recovery. So now we are talking little bit about what recovery here. My dear friends, let's talk about a final piece of puzzle that is called as recovery. So once a failure occurs, we need to plan to get the what system back to a what working state, right? So here I'm outlining three aspects of that recovery process. What is the first one? The first one is diagnosis. So the first step is always to figure out what went wrong. Diagnosis involves the detections of failures and locations of the failed components. So this is often done using heartbeat messages. Try to understand this. So we are going to use heartbeat messages. So where nodes periodically send signals to a central monitoring system. If heartbeat is missed, so it is an indicator of failure. Understanding my point, guys? So it will keep on sending heartbeats. So say even same in the case of what a name node also. So name node will be always sending heartbeats to the what different data nodes. So if any one data node is not replying to that heartbeat means, then name node will get to know. So there is a failure in name data node. That is a concept in big data analytics actually. And next one is backward recovery. So this is a very common and straightforward approach. The idea is to periodically save a consistent state of the system on a stable storage. So which is called checkpoints. So we are going to call it as checkpoints. Try to understand this checkpoint. So this is very, very important. And resume normal operation. Guys, when a failure happens, you isolate the what failed component and roll back to the what last checkpoint and resume normal operation. Okay, so think of it like a what video game. You save your progress every few minutes. And if you get a game over, you just reload from your last save point. The main drawback is that it leads to wasted execution time. So as you have to what redo all work since the what last checkpoint. And the last one is called as forward recovery. So this is a more advanced approach used in real-time and time-critical systems where you simply cannot afford to roll back. So instead of rolling back, the system state is reconstructed on the fly from diagnosed data. See here I've clearly mentioned that point. Okay, so this is much more complex and is often application specific, sometimes requiring additional hardware. Okay, a good example is an air traffic control system where rolling back is not an option. So guys, recovery methods vary and the choice depends on how critical your system is and your tolerance for wasted work versus downtime. This you have to understand, guys. So now we are jumping into today's session concept. So I think this will complete the what previous session concept. So till here everything is clear. Till here everything is clear. Okay. Okay, so guys, today we have to what discuss a few things on consistency, availability, and partition tolerance, and then we have to jump to cap theorem, and I have to give some examples on MongoDB and also Cassandra. We are not going to cover the entire concept on MongoDB and Cassandra. I'm going to give you only introduction, and finally we are going to explain big data lifecycle. So these are the concept we are discussing in today's session. Okay, I will go very fast, guys. So please, if you are not understanding any concept, then you can stop me anytime. Okay. So now can you tell me, before I'm going to start, so can you tell me what is consistency according to you all? So the very first thing is we are talking about consistency. According to your understanding, what do you mean by consistency? Consistency means what? I'm not okay. Consistency means a particular thing works as expected. Okay, that is the one definition. So degree of which data across multiple system databases locations is identical and accurate. Very good. Okay, yes. Okay, I think yes, many of them are trying to give what definition of consistency. So let me go with my definition. Okay, so now guys, so in the world of distributed system, we often deals with replicas or copies of data, so which are known as shards or partitions. Okay, so when you make a write, you need to update all the replicas. Remember this. So when you are going to do some changes, then you have to do changes to all the replicas. That is one of the very, very important thing. A big question for this is what happens when someone tries to read that data while updates are happening? Correct, no? Are you getting my point? You take this point in your mind and then answer for the consistency. Guys, consistency is a measure of whether a read of data item from any replica will always retain the latest, most recently written value. So this is a very strict definition. So think of a what bank account. When you deposit money, you expect to see that new balance reflected immediately, right? No matter where you check it. So this is the kind of consistency that traditional databases like RDBMS and OLTP systems provide. So this is governed by ACID properties. This complete thing is governed by ACID properties. See here, ACID properties. Okay, what is ACID? Atomicity, consistency, isolation, and durability. try to listen to me carefully, guys. In big data system, this level of consistency can be difficult to achieve at scale. So some system allow for more relaxed form of consistency. Okay, these system might allow to return an older value, but guarantee that eventually the latest value will be propagated to all replicas. So this is the principle behind base concept. So which stands for basic availability, soft state, and eventual consistency. So this model is often used in system of engagement like social media network and so on and so forth. Guys, we will talk about acid property and also base property in more detail in upcoming slides. But for now, remember, this is the key distinction. What is the key distinction? Acid property. Okay, acid is for strict, immediate consistency. Okay, let me write here. Strict and immediate consistency. What about base? So base is for eventual consistency. Okay, that favors availability and also scales. Okay, so now let's dive deeper into the concept of acid property. I think acid property you have learned in your DBMS, right? The same property I'm trying to explaining you here. I'm not going to spend more time to explain on this. So you just look at here, guys. So let me explain you one by one in detail. Okay, let me explain you one by one in detail. Okay. What is atomicity? So here definition is clearly given. What do you mean by atomicity? Guys, look at here. So this is the acronym for 4 key properties, right? Acid means acronym for 4 key properties. The first one is atomicity. First one is atomicity. Guys, this ensures that a transaction is all or nothing. So all operations within a transaction must succeed, or if one fails, the entire transaction is rolled back completely. That is called as atomicity. Guys, there are no partial transaction. Try to understand this. There is no partial transaction. So in the case of what? Atomicity. See, for example, when you transfer money from account A to account B, the debit from A and the credit to B are single atomic operation. It either both happens or neither happens. That is called as atomicity. And what about consistency? Guys, here the consistency definition is different. In big data, consistency definition is different. So both are not same. That's why I'm stressing here. Guys, this consistency guarantees that only valid data is returned to the database. Correct, no? A transaction can only move the databases from one consistent state to another consistent state. That is called as consistency. See, for example, if you have a rule that a bank account balance can never be negative, that is called as consistency. And a transaction that would make it negative will fail. Understanding my point, guys? And next one is called as isolation. So this ensures that the result of the transactions are not visible to other operations until the transaction is complete. We are isolating the data. We are isolating the what transaction here. So this is a critical for what? Concurrency control. So meaning that multiple transactions can happen at the same time without interfering with what each other. That is called as isolation. And what about the last one? Durability. So this is guarantees that once a transaction is committed, the results are permanent. So even if the system crashes, the data will not be lost. So once you get the transaction successful message, you know that, guys, you know that change has been what saved. Guys, these 4 properties are the bedrock of the traditional RDBMS. and are what give them their reputations for reliability and also data integrity. So how many of them agree with my point, guys? How many of them agree with my point? So this concept already have learned in SQL, right? So everyone will agree with my point. Can you all type agree on chat box once you're all agreeing? Okay, yes, thank you guys. So now we are jumping into next slide. See, next slide, I'm giving clarifications on consistency. Guys, this is the very important point. So I'm going to put 3 stars here. See, once I am taking 3 stars means this is very, very important for your examination point of view. Okay. Guys, it can be what source of confusion. So please pay close attention. Guys, the C in acid is different from the C in cap theorem. I already told you, right? So we are going to discuss cap theorem afterwards. But both are not same, guys. That you should remember. So they are related but not the same. The C in acid of RDBMS based on OLTP system. Okay, a C in acid is much broader concept. It applies to entire database and guarantees that a transactions involving multiple data items will not violate any of the database integrity constraints. So this is very strong and harder to achieve level of consistency. But guys, so we are going to learn C in cap theorem. Okay, so especially for most NoSQL system, we are going to use this. So this is a more focused concept. It applies only to the ordering of operations for a single data item. See here it is underlined. Okay, so not a transaction involving multiple data items. So it is a strict subset of C in acid. It is a strict subset of C in acid. So why is this distinction important? You can ask me, right? Guys, supporting the full acid semantics, especially the multi-data item transaction in NoSQL system can become a bottleneck. Okay, it requires a single transaction manager, which defeats the what purpose of distributed scalable system. This is why many big data systems relax the consistency requirement to achieve better performance and scalability. So when we talk about consistency from now on, unless I specify, so we'll be talking about the stricter single item consistency from the cap theorem. Understand this. Okay, now let's understand level of consistencies. So here we have what plenty of levels of consistencies. The very first one is called a strict consistency. So this is the most what stringent level. So it requires a real-time line ordered view of writes. If a write happens, all subsequent read across all threads must see that write immediately. Okay, so this is almost impossible to achieve in real world distributed system. Try to understand this. And second one is linearizable consistency. This is the more practical but still very strict model. So it acknowledges that writes take time to propagate. So it guarantees that any read will return the most recent write that was completed. The order of operation is still sequential, but it does not impose real-time ordering for overlapping operations. And next one is called a sequential consistency. This is a bit more relaxed. So it guarantees that all threads will see the writes in the same global order, but that order does not have to be in real time. Understanding my point, guys? See, for example, so if two writes happen at the same time, all clients will see them in the same order, but it might not be what exact order in which they were physically committed. And next one is called as casual consistency. So this is very useful and popular model. Okay. So it only orders writes that are casually related. So if a write to data item Y happens after a read of data item X within a what single thread. then all other threads must see the write to X before the write to Y. And last one is called as eventual consistency. This is the most relaxed model again. So which we have already mentioned in the context of Bayes theorem. So the guarantee here is that if no new writes happen for a while, all replicas will eventually converge on the latest value. So this is the ideal for systems like social media feeds, where a few seconds of inconsistency is acceptable. Guys, this spectrum is the key understanding the trade-offs we will discuss with the CAP theorem. Okay. So now you can see next time showing you what exact example of what's strictly consistent. Guys, let's look at an example to take these consistency model more concrete. So this slide shows a scenario with two data items. One is X, another one is Y. Okay. So initially, so we have to set X and Y is equal to 0. So we have four processes here. Look at here. We have four processes, P1 to P4. Okay. So P1 writes X is equal to 5. See, W means writes, guys. So P1 writes X is equal to 5. Then P2 writes Y is equal to 10. So these writes happen in real time. Now look at the reads. So process P3 reads X is equal to 5 and Y is equal to 10. And then process P4 reads Y is equal to 10 and X is equal to 5. Guys, look at here. Since both P3 and P4 read the latest value of X and Y, and the reads reflects the real-time order of the writes. So this schedule is considered. The meaning of this is what, guys? The meaning of this is strict consistent. So this is the holy grail of consistency. But as I said before, it is very difficult to achieve in large scale distributed system. Correct? No. The key takeaway here is that every process sees the writes in the exact same real-time order. Okay, now let's move on to the slight variation to understand the difference with linearization. Now let me take one small example to show this, guys. You just look at here. Let's look at the slight different scenario. Again, P1 writes X is equal to 5. Look at here. P1 writes X is equal to 5 and P2 writes Y is equal to 10. So these are our two real-time writes. Now let's examine the reads. Look at here where P3 is reading. So X is equal to 0 and then so Y is equal to 10. So P4 reads Y is equal to 10 and X is equal to 5. What happens here? Can anyone tell me what happens here? What happens here, guys? What P3 is doing? So right now the X value is equal to 5, right? But what P3 is doing? P3 is reading X is equal to 0. What is the meaning of this? Yes, it is reading X. What value of X it is reading? X is equal to 0, right? Not dirty read. It is not called as a dirty read. Yes, it is reading the initial value. So it is reading the old value of X. Correct? No, it is reading the old value of X. You're all understanding. See, X is equal to 0. X is equal to 0 is the old value of X. So, and then it is reading Y is equal to 10. So this is a valid state because the rate of X is equal to 5 took some time to propagate here. And P3's read happened in that gap actually. However, the reads are still consistent with the sequential ordering of the writes. So this schedule is linearized, linearizable. So it is not strictly consistent because P3 reads an old value, but it is linearizable because it is still consistent with some sequential ordering of the operations. So taking into the account the time it takes for writes to complete. Correct? No. The important point is that linearizability is a what practical approximation of strict consistency that accounts for network latency. Am I right or wrong, guys? And next I'm talking about sequential consistent. Now I'm talking about the example of sequential consistent. So let's continue our journey down the what consistency spectrum. Again, P1 writes x is equal to 5. P2 writes y is equal to 10. This time P3 reads, look at here, P3 reads x is equal to 5, y is equal to 0, and finally y is equal to 10. And P4 reads y is equal to 10 and x is equal to 5. Okay. So notice something interesting here. So P3 reads the new value of x is equal to y here. Correct? No, new value of x actually. That is x is equal to 5. But then it reads an old value of y is equal to 0. So before eventually seeing the what new value of y is equal to 10. The key here is that all writes are globally ordered, but not necessarily in a real time. P1 and P2 writes are considered parallel in the sequential order. Since P3 reads the old value of y, so this is not linearizable. How many of them will agree with my point? So this is not linearizable, right? This is not linearizable. So it is sequentially consistent because both P3 and P4 still see the what same global order of writes. So even though their real-time reads might not show it. So this is the good model for system where the absolute real-time order is not as critical. But you want all clients to see the what same sequence of events eventually. Okay, so now let us look at the what casual consistency. The fourth one, I'm talking about casual consistency. Let's continue with the same example. So P1 writes x is equal to 5 and P2 writes y is equal to 10. So now P3 reads P3 reads x is equal to 5 first and y is equal to 0 and y is equal to 10. And P4 reads y is equal to 10 and x is equal to 0. Look at here. X is equal to 0. So something different is happening here, right? P3 and P4 reads the value in different order. So this is not sequentially consistent. I can say directly, this is not sequentially consistent, but it is casual consistency. Why it is casual consistency? Because the writes to x and y are not casually related. So P2's write to y did not happen because P1's write to x. They are independent event. So therefore, there is no casual order to be what violated. And the schedule is fine here. Guys, this is popular model because it is a great balance between performance and also data integrity. I think everyone will agree with my point. Correct, no? It is a great example of performance and also data integrity. It guarantees that related writes are seen in the what correct order, but it gives flexibility for unrelated writes to be what handled more efficiently. Understanding my point, guys? And finally, we have one more that is called as eventual consistency. What is eventually consistency? Look at here, again same. X is equal to 5, but here, look at here, guys. So what P2 is doing now? So P2 reads x is equal to 5 and writes y is equal to 10. Notice here that there is a what casual order established, correct? No? So P2's write to y is casually dependent on its read of x value. So now look at the what reads from P3 and P4. So P3 reads x is equal to 5, y is equal to 0 and y is equal to 10. And P4 reads y is equal to 10 and r is equal to, sorry, x is equal to 0. So this schedule is not casually consistent because P4 sees the what write to y but not the write to x. So even the write to y was casually dependent on the write to x here. Guys, P4 reads an old value of x violating the what? Casual order. Of course, it is violating the causal order, right? So this schedule is an example of eventually consistency. Okay, it is not strict. Okay, linearizable, sequential, or even casual consistency. It is simply guarantees that eventually the system will converge on a consistent state if no new writes occur. So this concludes the deep dive into consistency concept. I hope these examples are good example to understand all different types of consistency. How many of them will agree with my point? So everyone will agree with my point. You all understood what exactly meant by consistency. Satya, you are saying you need to ask any question. I have seen you have raised your hand. Do you have anything in your mind to ask? No, right? Okay, fine. So now I'm jumping into second part of our discussion that is called as cap theorem. Guys, look at here. So we have arrived at the very important topic that is called as cap theorem. This cap theorem is very, very important for NoSQL concept. Okay, NoSQL, you have to learn MongoDB, you have to learn Cassandra means. So this will play a what crucial role in understanding NoSQL. So that's why this is very, very important topic. So this is a fundamental principle for distributed system, and it is known as Brewer's theorem. It is also known as Brewer's theorem. Okay, let me write here. Okay, after Eric Brewers. So who first articulated this? Guys, the cap theorem stands for three core properties of distributed database system. One is called as consistency, availability, and also partial tolerance. So look at here. The first C, I'm talking about consistency. So we just discussed, right? This means that a read from any node will return the what same most recently written data across multiple nodes. That is called as consistency. And what do you mean by availability? Availability means a read or write request will always receive a response, either a success or failure. So within a what reasonable amount of time. And the system is always available to service the request. That is called as availability. And what do you mean by partition tolerance? So this is the ability of the system to continue functioning even when there are network outages that split the what cluster into multiple isolated groups or silos. So this is known as split brain problem. Okay, let me write here. Yeah, here it is clearly mentioned. So this is known as split brain problem. Guys, the cap theorem states that a distributed data system can only provide two of these three properties at the same time. Try to understand this. So let me write this on your what PowerPoint. Two of these three properties at the same time. Not all three, guys. Two of these three properties at the same time. Okay, so the meaning of this is you can have combination of any two here. You can have CA, you can have AP, or you can have CP. So any two, but never all three. Understanding my point? This means that when a network partition happens, so which is a very real possibility in any large distributed system, you have to make a choice. So do you sacrifice consistency to stay available, or do you sacrifice availability to stay consistent? So this theorem is critical design constraint for all big data system. Okay, let us look at the what properties of each one by one. Okay, look at the diagrammatic representation. Now you'll understand clearly. So very firstly, we are starting with C. Guys, this slide shows a simple distributed database with three peers. So one is peer A, second one is peer B, and third one is peer C. So each peer holds a replica of the same data. Can you observe here? So ID 1, 2, 3 and amount the same value we have taken. Here also 1, 2, 3 amount we have taken same. Here also. The meaning of this is, so we have a what replica of the same data in all three peers. Inconsistent system, if you read a data item from any of these peer, so you will always get the same value. Correct? No? You read from here, you will get the same value. You read from here, you will get the same value. You read from here, you will get the same value. So this slide shows three users. Look at here. Three users it is showing. And all three are reading ID value of 3. So which is showing 49 for all, right? So this is the consistent state. Now we are all understanding with respect to big data what is consistency. Okay. So now look at here, guys. Next slide. Now, next slide, I'm talking about when can it be inconsistent. See, okay, here is where things can get tricky. Let's say a user writes a peer A. Okay, updating the value for ID is equal to 3. ID is equal to 3 from 49 to 50. See, he is updating a value. Now, before this, update can be propagated to peer C. Okay, another user tries to read ID equals to 3 from peer C. Because peer C has not received the update yet. So it will return the old value, correct? No? It will always return the old value, right? So this is the state of inconsistency. The two reads from peers A and peer C returns different value for the same data item. Guys, a strict consistent system would not allow this to happen. So it would make the user wait until peer C is updated before the read is allowed to happen. But as we will see, that's impact availability. Correct? No? Understanding my point? Now look at what is availability. Now look at here. Let's talk about availability now. Availability is nothing but A in cap theorem. Okay, the definition is very simple, guys. A request from a user to a peer must always get a response, either success or failure, within a what reasonable amount of time. Okay, think about peer C again. Say it gets disconnected from the network, perhaps due to what? A network partition. The user tried to send a request to peer C. Okay, peer C has two choices to maintain the availability. Okay, what are the two choices? So one is be available and second one is be unavailable. See here I've clearly mentioned be available and also be unavailable. These are the two partitions. Okay. So what is be available means? Be available means it can respond with the failure message immediately. The user's request fails, but they get a response. So the system is technically available for that request. What about be unavailable? So it can wait for the network problem to be fixed before responding. The user's request would just hang and eventually time out. So which is an unacceptable user experience in most modern systems. So in the face of failure, the system need to be what designed to respond quickly. Even if that response is a failure message. The core tenet of availability is that you don't make the users wait indefinitely. I hope everyone understood what exactly mean by availability. Next, we are moving into the what? Last one actually. That is partition tolerance. Okay, partition tolerance. Listen to me carefully now. Okay, so let's combine what we have learned. The real challenge. The real challenge comes when there is a what? Network partition. So this is when the network fails in such a way that the cluster is split into two or more groups that cannot communicate with each other. So look at the diagram. So look at the diagram given here. Okay. So this is when the network fails in such a way that the cluster is split into two or more groups that cannot communicate with each other. So look at your example. Peer A and peer B are in one partition. Correct? No. Peer A and peer B are in one partition and peer C in another partition. So now user wants to update. ID is equal to 3 on peer C. So both are in different network. This slide shows option 1 here. Okay, peer C cannot communicate with the other peers to get consensus on the what right actually. The maintain consistency and also availability. To maintain consistency and availability, it has to what reject the user's request. See, any access by the peers, any access by the user on a peer C leads to what failure message. So is it available? Yes, because it comes back with the response, a failure message. Is it consistent? Yes, it is also consistent because the user update is not processed. So the data on all peers remain consistent. Is it partition tolerant? No. Is it partition tolerant means? No, because it failed to service the what request in the face of partition. Okay, this is a CA. Okay, CA system, consistent and available, but not partition tolerant. Guys, traditional single load RDBMS system are good example of this. When they are partitioned from their clients, so they are unavailable. And look at here, guys, next slide is given the same thing. So it is giving what option 2. You can observe here. So I'm talking about option 2 now. So peer C decides to accept the update from the user and record it with the success message. Record it with the what success message. It does this even though it knows it cannot communicate the right to peer A and also peer B. So is it partition tolerant? Yes, it is partition tolerant, right? Because it continues to service the request despite the partition. Is it available? Yes, it is available because it responded with the what success message within a reasonable time. Next question is it consistent? No, it is not consistent. So the system has become inconsistent here. The data on peer C is now different from the data on peer A and also peer B. Correct? No? So this is an AP system. This is called as AP system. AP means what? Available and partition tolerant, but not consistent. Guys, many modern NoSQL databases like Cassandra, CouchDB are designed this way. They favor availability and partition tolerance, often providing eventual consistency. And what is the final option, guys? So this is the final option. That is called as option 3. Okay, option 3 means, look at here. Listen to me carefully now. See, peer C decide to be consistent. It refuses the process, the user's update until it can communicate with peer A, peer B and replicate the data. The user is made to wait here, potentially for a very long time, until the what partition is fixed. Now tell me, guys, is it partition tolerant? Yes, it is partition tolerant. Okay, because no update is committed until the what data replicated to all the peers, right? Then it is partition tolerant. Is it available? Yes, it is available because no update is committed until the data is replicated to all the peer system. Now my last question is, no, sorry, this is consistent. Sorry, it is consistent because no update is committed. No update is committed means consistency. My last question is it available? No. So this is not available because no update is committed until the data is replicated. Sorry. No, the user request is delayed here. The user request is delayed for all practical purposes. The system is unavailable in this case. Correct? No. So this is CP. This is CP system, consistent and also partition tolerant, but not available. Guys, many NoSQL databases like MongoDB, HBase are designed as CP system. Okay, so in the face of what network partition, you must choose. So this brings us back to the CAP theorem. So hope till here everything is clear to everyone. So till here everything is clear, guys. Can I get quick confirmation on chat box? Now I will show you CP theorem, CAP theorem. Now look at here. This is the CAP theorem. You all can observe here. So this slide restates the what core of CAP theorem. So which we have just proven with our examples. A distributed data system can only provide two of the three properties. See, look at here. Two of the three properties, either CA or CP or AP. With example, I have shown you, right? Correct now? With example, I've shown you everything, right? Okay. This is very, very important point, guys. When there is a partition, the system has to decide whether to pick consistency or availability. Okay. So this choice is fundamental to the design of the databases. Okay. So we have CA system here. So we have CP system here. Look at here. Where is my pen? Okay. So we have CA system here. We have CP system here. We have AP system here. CA system is a system that works great as long as there are no network partition. It is consistent and available, but it will fail when a partition occurs. That is CA system. What about AP system? What about AP system, guys? What about AP system? It is a system that remains available and partition tolerant, but in the event of the partition, it may become inconsistent. And the last one is called a CP system. The system remains consistent and partition tolerant, but in the event of partition, it may become unavailable. So this is three different theorem we are going to use in CAP theorem. Okay. See here, each slide is explaining consistency or availability choices. And this is the database option. I will directly jump to database option because this is very, very important slide. Guys, this slide gives you a great overview of where some popular databases fall on the CAP theorem. Okay, the design choices of these big data databases reflects the reality that faults are likely to happen. What is the first one? First one is CA. CA means what? Consistent and available. So these are your traditional databases. What are those traditional databases? PostgreSQL and MySQL. So they are not designed to be partition tolerant. Understand? With example, we are showing you here. And next we have AP here, available and partition tolerant. So the best example for this is Cassandra, CouchDB, and also DynamoDB. Okay, this is DynamoDB. And with respect to CP, so we have three more. So one is HBase, MongoDB, and Redis. These are the three actually. The choice of database depends entirely on your use case. So do you need the absolute latest correct data at all time? So like in banking application, then CP or traditional CA system is for you. So do you need your system to be always up and running? So even if the data is few seconds old, so like in social media feed, then you have to go for AP system. Okay. So this flexibility to choose the right behavior for your application is the key advantage of big data system actually. So even in your examination also, guys, so I'm going to ask you the same type of question. So then you have to name whether it is belongs to CA or AP or CP. So hope this is crystal clear to everyone. Guys, one definite question you are going to get in your examination. I'm telling you guys, one definite question I'm going to ask you in the examination. Okay. So this is very, very important concept. So have you all understood? Okay. So quickly, without wasting time, now I'm jumping into next concept. That concept is called as base concept. Guys, we have talked about acid, so which is the principle behind consistent system. So now let's talk about base. So which is design principle for AP databases. Okay. AP databases that use distributed technology. Guys, the acronym of this is basically available soft state eventual consistency. Okay. So basically available means the system guaranteed to be what available. So it will always respond to a request. So even if it is with the what failure message, that is basically available. And second one is called as soft state. The state of the system can change over a time even without new writes. This is because changes are being propagated throughout the system to achieve eventual consistency. And finally, we have eventual consistency that is written by E. So as we discussed, the system will eventually become consistent if no new writes occur. So what is the key takeaway? That base is here favors availability over consistency. That is the first one actually. The meaning of this is it is not suitable for transactional system. Okay, where lack of what consistency is a concern, but it is perfect for write heavy workload. It is very, very important for write heavy workload like your social media or monitoring data, where reads don't need to be what consistent in a real time. Okay, see next slide, I'm going to what break this into different part. So the very first one is basically available. So let's go one by one. So that is represented by BA, basically available. Okay, guys, this slide shows a distributed database with three peers again, A, B, and C. So network failure has caused a partition. So splitting the system into two groups here. So this is one group and this is another group. We can call it as partition A and partition B here. Clear? Now notice that even with the partition, user A can read data from peer A, and user B. Where is user B? So here we have user B, right? So here we have user B, right? User B can read data from peer C. So both users receives a response despite the network failure. The database is available to both partitions. So this is what it means to be what basically available. Okay, the database will always acknowledge a client's request either with the requested data or with a failure notification. So it will not make the user wait indefinitely. That's why it is called as basically available. Hope everyone understood what is basically available. And next one is what is the safe state? You have to understand with the example, right? So next, yes is safe state here. Let's say user A. So let's say user A update a record on node A. So before the what update can be propagated to the other nodes. And user B, look at here, user B requests the same record from peer C. So because the system is in a what soft state now. So it can return the data from the peer C even though it is a stale. So this state of system is inconsistent across its peers. A database that is in what soft state is one where data can be in an what inconsistent state when it is read. The result may change if the same data is requested again. Okay, because the update could have been what propagated in the meantime. So this is the key difference from strictly consistent system and also
the soft state actually. So now look at the what final part of the base. What is that? Eventually consistency, right? So that is last E. Actually, it is called as eventual. This property guarantees that the database will be what eventually become consistent. Okay, let's re-examine the scenario we have taken before. So user A updates record on node A. User B requests the data from the peer C before the change has been propagated, and that get what stale data. Now let's say a bit of time passes and the changes are successfully propagated from peer A to peer C. Now a new user, that is user C, requests the same data from the peer C. Okay, so this time they get the what correct and updated value. The database only attains consistency once all the changes have been propagated to all the nodes. While this propagation is happening, the database is in soft state. Okay, so this model works well for applications where a few seconds of inconsistency is not a problem. See, for example, if you post a comment on social media, you might see it immediately, right? But your friend on the other side of the world might see it a few seconds later. That is the what perfect acceptable, and it allows the what system to be what highly available and scalable. Very simple. Okay, now let us take here few examples. So MongoDB and Cassandra examples we have taken here. Okay. Okay, let's start with the very first one, MongoDB. So this is the MongoDB picture, guys. So MongoDB is a very popular NoSQL database. We all know about that. It is a document-oriented database, okay, that stores data in flexible JSON format. So it is going to store data in the JSON format. This is the format we are going to use in what MongoDB. Okay, it is going to store data JSON like a what document here. A key features of MongoDB is its flexibility in handling consistency. Okay, so it provides various reads. Listen to me carefully. It provides various reads and write choices for flexible consistency trade-off with scale, performance and durability. Performance and durability. So this is what makes it so versatile, guys. By default, MongoDB belongs to which system, guys? So is it belongs to CA or CP or what? MongoDB. I have explained you, right? So this is belongs to CP system, right? This is belongs to CP system. This means it prioritizes consistency and partition tolerance. It uses a primary secondary architecture. Okay, it has an automatic primary re-election on primary failure or network partition. The meaning of this is it ensures that even if the part of the cluster fails, it maintains a primary node that guarantees consistency. Okay, so now next look at here. This is the MongoDB diagram. You can understand by looking at this diagram. So this is the MongoDB cloud interface. So now I want you to what focus on a couple of key things here. First, notice the cluster tier. Okay, so first you all notice the what cluster tier. So M0 sandbox. and type replica set 3 nodes. And type replica set 3 nodes. So this shows that, so we are running a replica set, so which is MongoDB way of providing high availability and data redundancy. Okay, a replica set is a what group of MongoDB processes that maintain the same data set. So one is the primary node, and others are secondary nodes. Look at here. See, one is the primary node and others are secondary nodes. Understanding? And you look at the second image. So this also shows an example of JSON documents. Okay, JSON documents. Okay, you can see its document. You can see this document. Document-oriented databases. So we are going to call it as document-oriented databases. So this is showing read with, see, look at here. So read with read preferences. Okay. And sometime it is going to show, so read with write concerns also, which allows developers to choose their desired level of consistency. Okay. So now you can recap what is casual consistency. I have explained you about casual consistency, right? So before we dive into MongoDB specific consistency settings, let's quickly recap what is casual consistency. We discussed this earlier, right? So it is very important model for big data system. So remember, a system is casually consistent if it guarantees that if a write happens after a read in a single thread, all other thread must observe those operations in the same order. In the simpler term, so if a user sees a new comment on a social media post, then likes it. So all other users must see the comment before they see the like, right? The like is casually dependent on the comment. So this model is great balance between strong consistency and also performance. Okay, it allows for a more relaxed approach than strict or linearizable consistency while still maintaining the integrity of casually related events. Understanding my point, guys? Yes or no? Guys, I'm going to talk more on this MongoDB. So when I'm going to teach you MongoDB concept. So here I just taken this for an example. That's it. Okay. So all these example we have taken for introduction purpose. That's it. Okay. So all this concept I will explain later, guys. So now I'm telling you means you will not understand. That is the main concern. Okay. So if you want me to explain case 1 and case 2, I will explain you. But definitely I'm going to tell you, you're not going to understand it. So once I'm teaching MongoDB, then see, I will give you, before I'm going to teach you that, I will give you all the information about the basic needs of requirement of MongoDB. Then I'm explaining you MongoDB means you'll understand. You'll be in a position to understand. Okay. So if you want, I will explain you both the cases. So for a time being, that's it. This is no casual consistency case. So look at the concrete example from the MongoDB. Okay, so a full details of the example are quite involved, but the key takeaway is this. So without a special setting, MongoDB might not guarantee casual consistency. Understanding my point, guys? So a read on a secondary replica could return an old value even if a write on the primary happened just before it. So that is case 1. I will skip this slide, guys. I don't want you people to confuse now, because this is not so important right now. Okay. So this is about read concern and also write concerns with respect to MongoDB. This is write concern. And consistency scenario also mentioned here with respect to that. This is on Cassandra. I will give you introduction on Cassandra like your MongoDB, and remaining all concepts are not necessary right now. Okay. So otherwise you go through it, guys. So this is the documentation I'm giving you. So before I'm going to explain you each and everything. That's it. So now we have what Cassandra concept. We all know this is another popular NoSQL database, but it is fundamentally different from MongoDB. So here we are going to use key value store with columnar storage. So we are going to use a columnar storage concept here, and key value store we are going to use here. The architecture difference is that there is no primary replica. Okay, so every node is peer here. So this gives Cassandra high partition tolerance and also availability. High partition tolerance and availability. So, and it allows for a very flexible set of consistency level. Okay, so you have to observe here. A read or write operations in Cassandra can be configured to use different consistency level. Okay, look at the few of them. First one is 1, 2, 3, all. So the operation is considered successful when 1, 2, 3 are all replicas respectively have acknowledged it. And next one is quorum. Okay, so this is a very common choice. The operation is successful when a majority of the replicas have acknowledged it. And last one is local quorum. So a majority within the same data center must acknowledge the operations. Guys, Cassandra design is heavily influenced by CAP theorem. So it comes under AP system. So this comes under AP system by default. So favoring availability over consistency. But it allows you to tune the consistency level to meet your application's need. Okay, this is a very, very important concept. Okay, even so we are going to learn more on Cassandra in the next coming slide. Okay, and you can see here I have taken few examples. Okay, let me explain you this example. So see here, how would achieve, see, suppose you can ask me, sir, how would we achieve this casual consistency here? Correct, no, in Cassandra. Guys, what I'm going to say here is, see, look at here. Here we have taken the example. Pick read consistency level or write consistency level should be equal to quorum. So why does this work? Guys, a quorum is a majority of the nodes. Okay, if a write operation is acknowledged by a majority of nodes, a read operation is also acknowledged by a majority of the nodes. Okay, so then there is a mathematical guarantee that the read and write sets will overlap by at least one common node. So this means a read will get the last write of the data item. Okay, so let me take one small example to explain on this. Okay, so for example, in a 5-node cluster, okay, you just imagine, so we have a 5-node cluster. 1, 2, 3, 4, 5. 5-node cluster. Okay, a quorum is 3. Okay, so if a write goes to nodes 1, 2, 3, sorry, 1, 2, 3, not 5, 1, 2, 3, and read goes to node number 3 and 4 and 5. The node 3 is the common node here, right? What is the common node here? Node 3 is common. The read will see the write here. Now, what if we use local quorum for both? If there is no overlap between the read and write sets, then we fall back to eventually consistency. This shows you the power of flexibility of Cassandra's architecture. So it gives you the control to choose the exact trade-off you need for your application. So which is a perfect example of CAP theorem in action. Okay, so this is about Cassandra, guys. This is about MongoDB. I'm giving you only introduction on Cassandra and MongoDB. That's it. And finally, so we have to cover big data life cycle. So I'm planning to cover big data life cycle now. With this, I'm going to complete today's session. What is there in a big data life cycle? So quickly look at here, guys. Quickly look at here, everyone. What do we have in big data life cycle? Guys, already we have gone through big data concept, right? So we have talked about technical foundations of big data system, but how do we apply this in the real world? This is where big data analytical life cycles comes in. Okay, so big data analysis is the different from traditional data analysis because of the characteristics of volume, velocity, and variety characteristics. So it is not as simple as querying a single database. Okay, therefore, we need step-by-step methodology to organize and manage all the activities involved with acquiring the data, processing the data, analyzing the data, and purposing the data. Okay, this is a structural approach that ensures your project is well organized and has a higher chances of success. Okay, so next slide, look at here. We have taken one small example to explain on this. So look at the example. Now you will understand clearly. Okay, so this is the relatable example to understand the big data life cycle. Imagine market research firm. I'm taking this, guys. Market research firm that runs survey for its clients. Say a company that makes LED TVs. Okay, so these surveys contain both structural data. Structural data means it will be containing numerical value, Boolean value, categorical value, grade value, so on and so forth. So you can take age, gender, rating, so on and so forth. And they are taking unstructured data also. So like free form text comments, that is comes under unstructured data. Okay, the survey is rolled out to large number of users from the various demographics. The firm collects the results and analyzes them to get a business insights. So often using multiple tools. Guys, these insights are then presented to the client who uses them to make critical business decisions, like what features to include in their new TV model. Okay, now think about the data here. So let me take one by one. So I am going to take the volume. So volume, the survey is rolled out to many users, that is volume. And what is variety? What is variety here? Variety means it contains both structured data and also unstructured data. That is called as variety. And what about velocity? So velocity is nothing but what? The data is coming in quickly from the live survey. So this is the perfect example for big data problem. Okay, so now we will walk through different stages of big data. So in big data life cycle, you can observe here. So clearly this slide is showing different stages of big data. So one is business case evaluation, data identification, data acquisition, data extraction, data validation and cleaning, aggregation and representation, analysis, visualization, and finally analysis result. These are the different stages available in the big data system. So this is a comprehensive end-to-end methodology. You can think of it as a roadmap for any big data project. We will now go through each of these steps in detail. Okay, let me explain you one by one. So by taking some real-time example. So this is the very first one, guys, business case evaluation. Okay, this is the very first step of any big data project is to ask a foundational questions. So actually in previous class, one of my friend was asking the question, right? Sir, how can we convert the normal problem into big data problem? So by understanding this, you can convert normal problem into big data problem. So for that, you have to follow all these steps. That's it. So what is the first one? Look at here, guys. Is the business problem you are trying to solve really a big data problem? That question you have to answer first. So this stage is crucial because it ensures you are not wasting resources on a problem that does not require big data solution. Guys, a big data business problem needs to be what directly related to one or more of the big data characteristics. Okay, so it has to relate to volume, velocity, and variety. See, for our TV example, we need to determine if the survey data has high volume and variety. This stage should begin with a well-defined business cases. Correct? No. Well-defined business case is also very, very important for us here. You must have a clear understanding of the justification, motivations, and goals. Okay, you must have a clear understanding of what? All these three of analysis. You should also identify what business challenges the analysis will tackle and what KPI. KPI is nothing but what? Key performance indicator you will use to measure the success. Understanding my point, guys? Think about this, guys. For our TV survey, the business question might be, what features are most appealing to young adults? Or what price point should we target for a specific market segment? So once you confirmed that it is big data problem, you have a what clear business case. You can move to what the next stage actually. What is the next stage? Next stage is data identification stage. Okay, this is the second stage of what? Big data life cycle, correct? No. The main objective here is identify the data sets required for the analysis project and their resources. Both are very, very important. So in our TV survey example, the primary data source is the survey itself. But we might also need other data. See, for example, the client might have what list of past survey users with demographic attributes, right? So we might also need to look to the what other surveys or third-party data from external sources. A very important point here is that while a wider variety of data sources can help you find hidden pattern, you must be cautious. Too much data variety can also confuse the analysis. And that is going to what? Lead to the overfitting problem. That will lead to the what? Overfitting problem. So this stage, you compile a list of all the potential data sources, both internal and external. Internal means like your internal data mart. External means like publicly available data sets or blocks. So once you have identified your data sources, you are ready to acquire data. That is the third step, data acquisition. My dear friends, this is where we actually get our hands on the data. The third stage is all about gathering data from the sources we identified. So once the data is acquired, so we move to the filtering process. This is where we remove corrupt or unusable data. Guys, for our survey example, this might mean removing responses with empty fields or non-sensible values. For unstructured text, a lot of acquired data might just be what? Irrelevant. That is, we are going to call it as noise, right? So that we have to remove here. So it is a good practice to store verbatim copy of the original data set. So before you start what filtering, just in case you need to what go back. So this stage also deals with how you store the data. Okay, see for example, batch analytics. The data is usually stored on the disk first and then analyzed. But for in case of what real-time analytics, the data is analyzed first and then persisted to the what disk actually. So once the data is acquired and initially filtered, so we are ready for the next step. What is the next step here? The next step is called as data extraction. Data extraction. This is the fourth stage of your big data life cycle. This stage is dedicated to extracting data and transforming it into a format that can be used by the big data solutions. Let's get back to our example, TV example. So in our TV survey example, This would mean taking the what unstructured, free from text responses and structuring them. For instance, if a user writes that TV's sound quality is awesome, so we need to extract sound quality and awesome and turn them into what structured format that can be analyzed. Okay, the amount of extraction and transformation required depends on the type of analytics you are doing and capabilities of your tools. Understanding my point, guys? Okay, this step is a key part of ETL. So this is a key part of what ETL, extract, transform, load. Okay, so extract, transform, load process that you might be what familiar with from the what traditional based databases. Guys, once the database is extracted and transformed, now what we have to do, guys, we need to what make sure it is valid and also clean. See, look at here. Next step is data validation and also cleaning. Guys, this is another very, very important step in big data lifecycle. Okay, it is one of the what critical stage actually. Invalid data can skew and falsify analysis results. So this stage is all about making sure our data is ready for analysis. So it can be very difficult to establish validations rules for big data, especially for unstructured data. So this stage is where you establish complex validation rules. Correct? No. Complex validation rules. Okay. So complex validation rules to what? Remove the invalid data. In our survey example, this might involve identifying contradictory answers in the survey. Not only identifying contradictory answers, guys, identifying population skews. So for example, if the responses have an inherent gender bias, so that we don't make misleading gender-based analysis. And next, codifying certain columns for easier analysis. Guys, big data solution often have redundant data. Remember this. So it could have what? Redundant data. So which can be exploited to fill in missing valid data. So for batch analytics, so this can be done offline with ETL operations. Okay, ETL process. But in real-time analytics, you need a more complex in-memory system that you can use Spark concept actually. Then what is the next stage? Next stage is data aggregation and also representation. Guys, this is the sixth stage of your what big data life cycle. So data aggregation and representation, this is dedicated to integrating multiple data set to create a unified view. Let's take our TV example. In our TV example, this is where we would merge the survey's responses with a list of user demographics from the client databases. Guys, we would join these data sets on a common field, like a user ID. So we might also need to what? Reconcile data from the different sources. See, for example, one data set might label a field surname, while another labels it last name. Okay, so this can be what? Very time and effort intensive operations because of the what large volume of data. So it often requires complex logic to execute it automatically. Then what are the good practice we have to consider here? So we have to consider future data analysis requirement. Correct, no? Future data analysis requirement is very much essential here. Correct, no? So this is used to what? Foster data reusability. So you want to create a final well-represented data set that can be used for multiple downstream analysis. Now tell me, guys, once our data is clean and it is in unified format, so we can finally get to the what fun part. So that fun part is called as analysis, data analysis. Correct? No, that is called as data analysis. Guys, this is the seventh stage of your big data cycle actually. So this is where we finally carry out the what actual analysis task. So this stage is often iterative. Okay, iterative in nature, especially for exploratory analysis. Okay, the analysis can be as simple as writing a word query to compute an aggregation, or as complex as using the word data mining or statistical technique to discover patterns and anomalies. So let's get back to our example, guys. Writing, see, in our TV example, this would involve writing SQL queries to what compute aggregates and create charts. For example, what is the average satisfaction score for users in specific age group? So we have to use what? Some calculation, right? Building model to test hypothesis or make predictions. See, for example, can we predict which feature a user will like based on their demographics? So this stage is all about using your skills to uncover the insights hidden in the data set. And what is the next stage? Confirmatory or exploratory data analysis. Maybe you have heard about this, EDA. Okay, so this is called as CDA. This is confirmatory data analysis. And this is called as EDA. Either we will go with this or we will go with this. Guys, this CDA is a what? Deductive approach. You start with the what? Hypothesis and then analyze the data to prove or disprove it. The analysis is very focused and unexpected findings are often ignored. A good example is testing if a new TV feature is preferred by young males. So you have a what specific question, you analyze the data to find the answers. And what about EDA? Maybe you have heard about EDA, right? Exploratory data analysis. So this is inductive approach. Alva, this is inductive approach, closely associated with data mining concept. You don't have a specific hypothesis. So instead, you explore the data to discover patterns and anomalies. So this might not give you definitive what answers, but it can provide what general directions and lead to new insights. Guys, what I would like to say here is both the approaches are valuable. Okay, so CDA is great for scientific specific questions and EDA is great for uncovering new hidden insights. So often a project will use both in an iterative fashion. Okay, so once the analysis is complete, we need to what? Communicate the results effectively. By using what we are going to communicate, guys? So by using data visualization, we are going to communicate with the users. This is the 8th stage. Okay, so the ability to find great insights in your data is useless if you cannot communicate them effectively to business users who need to make decisions. Correct? No? I think everyone will agree with my point. This stage is dedicated to using data visualization techniques and tools to what graphically communicate the analysis result. Guys, in our TV example, so this would mean creating a chart and dashboards to show key findings, like the top features that appeal to each user segment based on gender and age. Guys, what I would like to say now is good data visualizations can also allow users to perform visual analysis where they can discover answers to questions they have not even formulated yet. So it is also crucial to provide ability to drill down and simpler statistics so users can understand how the aggregated results were generated. Okay, the choice of visualization technique is very important as the interpretations of the result can vary based on how they are shown. Correct, no? And finally, what is the last step, guys? What is the last stage? Utilizations of analysis result. The final stage of the life cycle is utilizations of the analysis result. So this is where we determine how the processed analysis data can be further leveraged. The analysis results are not just for one-time presentation. They can produce models that encapsulate new insights. New insights about what? New insights about the what patterns and relationship in the data. And these models can be used to improve business proposals and application logic. Guys, our TV survey examples, the reports and models we built are reusable assets. Everyone will agree with my point, right? The insights could be fed back into what enterprise system to optimize their behavior. For instance, on online store could use a what model to generate product recommendations for customer based on their demographics. So the result can also be used to optimize business processes. See, for example, the analysis could help a company consolidate transportation routes. Our results could be used to create alerts that inform users via email or SMS about events that require their attention. Guys, the final stage is about making sure the value you have extracted from the data is put to good use. So these are the 9 different stages of your big data, guys. And utilizations of results are not necessary. Okay, this is already explained. The last one is summary, guys. So I think that I have exceeded 8 minutes. No problem, guys. So finally, I came to the end of your session 4 concept. So this and all we have discussed in the in today's session. So this is the summary. And next session, so we are going to focus more on distributed programming. Okay, so that's all for today's session, guys. So if you have any questions on today's session, you can ask me now. I think last concept I've covered very fastly, right? What is the doctor server? I don't know doctor server. I have to search on that word. So last question. See, I have explained you big data lifecycle, right? So in your examination also, I'm going to give you one problem statement. So for that problem statement, you people have to what? Go with all 9 stages. So as I explained you today, you have to explain in your examination. That's it. So is it clear to all? Sakshi, you have raised your hand, and Reddy also raised your hand. What is your question? Do you have any questions to ask? When restoring a MySQL dump, if a duplicate key error occurs, the process stops. But however, in MongoDB, okay, maybe he is giving some example. Is it the example MongoDB restoration continues even if there are replicate? Yes, can you put the same question on discussion forum? Now I'm a bit tired actually. So please check chart from last 30 minutes. It is almost same word actually. Disaster recovery server and failover server both are same almost. Yeah, whole class is fast. I have explained you, right? See, that's why I told you. So to cover basics, I have taken much time. So now I am explaining you the advanced concept. In advanced concept, I am a bit fast. But you can go through the recordings. In recordings, you can listen again and again to understand each and every concept. I know actually I got many questions on chat box today. So I will do one thing, guys. I'm going to answer each and every questions. So in your discussion forum, is it okay? Today I took 6 hours classes. So I'm a bit tired today. So we are new for these things. So if concepts are clear, then only we will be able to understand and perform well. Of course, yes, Rahul. Who told no? That's why first 3 sessions I explained fundamental concept very slowly, right, Rahul? Why? What happened? Why it is your third class, Rahul? Ravi Kumar? I can understand. But today mostly points. Okay. May I ask why mics are not enabled in your sessions? So for others, see, I can enable my mics. Suppose you people are asking questions in the middle and continuously I'm answering means, then I'm not going to get a time to complete the syllabus, right? Saini, you are understanding? But today most points are not clear. What points are not clear? You people are talking about your what? Questions on chat box. Okay, I will do one thing, guys. I will go through your questions on chat box. I will answer you in the discussion forum. Is it okay? Is it okay for you all, guys? Or else you can put your questions on discussion forum. I will answer to each and every question. So is it okay for you all, guys? See, after Cassandra, I have explained you only big data lifecycle. That's it. So big data lifecycle is very easy. Two-way communication is needed. Priyanka, if I go with two-way communication, then definitely I will tell you I am not going to what complete the syllabus. So better, guys, you all go through the recordings. So once you are not understanding any of the concept, guys, actually I am telling you, so these are all basic concept. See, fundamental concept I'm covering. Okay, so next onwards we are going with what tools. So once we are going with tools, the same concept is repeatedly explained. No need to worry about that. Yuvraj, please go through the recording. So once you're not understanding, put a question on chat box. Put a question on what? Discussion forum. Okay, I will answer to your question there. I request each and everyone to go through the recording once. So once you people are not understanding any of the concept, you come back to me. Okay, you come back to me through what? Discussion forum. So we can what solve each and see, this is my job. I am going to give you what solution answer to each and every question. No need to worry about that. So please try to understand, guys. Sir, if possible, please share all PPTs till 8th session. So it will be bit helpful for us. Rahul, I can share, but what is the use of sharing all PPTs? You people will not read, see, you people will not get time to what read each and everything, right? See, one session before I'm uploading the PPTs, is it? In advance, I'm uploading everything, right? Today, I'm going to upload 5th session PPTs. See, every time I'm doing the same thing. In advance, I'm uploading all the PPTs. Correct? No. What is the purpose of uploading all 8 session PPTs now only? Why you need that? Hmm? Understanding, Rahul? So next time taking 5th session concept. So 5th session concept, I'm going to upload in advance. Okay, guys. So that's all for today's session. After upload, please share the link here. What link you want me to share, Ravi Kumar? I'm not getting. What link you want me to share? Hmm? So you have an access to your Tuxila, right? See, I will show you guys. I will show you. So once you are clicking on Tuxila, see, this is how you're going to see. Maybe you will be having access to this Tuxila, right? You click on Tuxila. Once again, it is taking time. So once you're clicking on Tuxila, server is a bit busy today. So here we are uploading each and every slides, right? Look at here, guys. Big data session 1, all 3 classes slides are uploaded here. Session 2, I have uploaded all. See, without annotation means 1 week before we have uploaded. So with annotation means after the completion of class. Same thing with 3 also. Same thing with 4 also. See, 4 is what? Placed in advance. So next, today I'm going to what? Upload the annotated one. So in advance, I'm going to upload session 5 concept. So from here, you can download, right, very easily. What link I need to share here? I'm not getting Ravi Kumar. So you can directly access that slides, right? Hmm? Ravi Kumar, are you there? And even parallelly, I'm storing, see, parallelly, I'm sharing all the PPTs in Microsoft Team also. So anything else, guys? Guys, whatever the questions I have not answered in today's session, so I'm going to copy each and every question and I'm going to put the same question on what discussion forum and I will answer you guys. No need to worry about that. So today only, see, after completion of this class, I'm going to copy each and every questions and I will answer to each and every question. So is it okay for you all? I will put all the questions in discussion forum. Otherwise, you people put a question on discussion forum. So we are there to answer. Okay, my team is there to what? Answer to each and every question. So even I will check and I will answer, guys. No need to worry about that. I don't want you people to what? Get in confusion status. So my main intention is you have to understand each and every concept in detail. Correct? Correct? Correct, right? Correct, right? Since we are all approaching to midterm examinations, so we have to complete the syllabus. So I don't know what other people are doing. I am taking too much of time to what explain each and every concept. A request from my side, let's not rush through the content. Then Hari, I'm explaining you same thing again and again. So I'm lacking one session concept. So when I'm going to complete the syllabus, can it be reduced? No, it is not possible. Once your handout is ready, and once so we have what published in Tuxila, then we have to follow the same thing. I'm doing that, right, Pradeep. So every week you are attending my class. Am I not doing that? Pradeep, I don't know why you people are sending so many messages regarding your chat box. See, I answered, right? So definitely I'm going to answer each and every questions. Since I was in hurry, I did not see your chat box. That's it. But every week I'm looking at your chat box, I'm answering, and then I'm continuing, right? Okay, I'll promise you guys next class onwards, I will be looking at your chat box. Is it okay? Is it okay for you all? Okay, guys, that's all for today's session. So if you have any question on today's session, you can use your discussion forum. So I'm going to give you answer to each and every questions. I'm repeating you. And next class, we are going to discuss on distributed programming. So all of them, just confirm with your lab access and try to go through lab lab tools. Okay, try to understand lab tools. Yes, I will be taking one extra class to explain each and every lab experiments. Okay. No, discussion forum is on your Tuxila. See, guys, actually, you have discussion forum here. So click on general. So in general, you have general discussion forum, and you have one more question and answer forum also. Either you can put your questions on question and answer forum, or you put your questions on general discussion forum. So better you have some questions means you put on question answer forum. So I'm going to answer each and everything. Okay. Otherwise, you put everything on general discussion forum. Okay. You use either this or this. So we are there to answer you guys. So we are there to answer. Okay. Not on Microsoft Team. Don't use Microsoft Team. Microsoft Team only for your class. That's it. So any questions you have, guys? So no questions means we can wind up today's session. If I ask one line feedback on today's session means you will give so many complaints on chat box. No problem, guys. Give me one line feedback on today's session. Okay. So whether it is positive or negative, so please give me one line feedback on today's session. So with your feedback, I'm going to stop the session today. Okay. Thank you all, guys. So have a nice day. Good night.